Yeah. So hello everyone. So this is our computer vision project presentation. It's me, Arghadeep, and Shankar. So we worked on facial emotion recognition with deep neural networks. Uh, yeah. So as you know, facial expressions play an important role in our daily human communication. And automatic facial expression analysis is an important area for with several potential applications. Now, there are many issues with facial emotion recognition, like uh, occlusion and lighting and uh, variant poses, identity bias, insufficient qualitative data, etc. So our goal in this project is mainly to work with images that have some sort of occlusion or pose variance in them. So, for example, uh, it could be somebody is wearing sunglasses or has a hat, or somebody is covering part of their face with their hands. So our goal is to still be able to detect their emotions even despite these occlusions. So we are, so we have mainly followed the paper by followed this paper, region attention networks for pose and occlusion robust facial expression recognition. And yeah, so the main goal is to uh, work on basically real world face images so that we can detect emotions even when there is some sort of obstruction or the face is not fully visible. And yeah, so the data set we have used for this is the FUR plus data set. The FUR plus data set contains the 35,048 by 48 face images, out of which we have kept 32,000 for training and 3,000 for testing. And there are mainly 9 categories that these images are classified into. So like 9 expressions. So like we have 8 emotions and then there is one left for unknown. So the 8 emotions here are neutral, happiness, surprise, sadness, anger, disgust, fear, and contempt. And we also have one more for unknown, which if it doesn't fit any of the above descriptions. Also, one more thing is that uh, the paper also has, so the FUR Plus actually doesn't have specifically have images for occlusion and pose variance. So what the authors of the paper have done is they have manually selected some images from the FUR Plus dataset and annotated them as to whether they are occluded and whether they have any whether there's a pose change. So that is so that is about the data set. And then Shankar will just go over the network.
Uh, Hello.
Oh, sorry.
Arghadeep will go over. Yeah. So
My bad.
I'll explain what the core idea of this paper is and what exactly the function, what exactly is the framework of the architecture of the network that we are going to present. So 1 second. Yeah. So as you can see in this slide, we have what is an illustration for the framework of the entire network. Now, this looks complicated at first, but we'll go over each part by part. So the network framework that we have, it's called the region attention network. So can you go to the next slide? Yeah. So this is the first part of the network, and this is also why where the name comes from, the attention part. So attention networks in general are a kind of network in which the instead of passing the input as a whole, uh, what you do is take regions of the image and pass it individually to the neural network. In order to do this, the idea behind this is that the neural network, this assigns weights to different regions, and the neural network can focus its attention on specific parts of the image that accurately portray whatever the classification is intended. So in here, what we are doing is we are cropping the images into a certain number of parts, and we are passing each of these cropped images into, next slide. We are passing each of these cropped images into a base CNN. So for now, we'll keep this base CNN to be a black box, but we'll later describe what we are using here. So the core idea is that these base CNNs are take different regions of the image and output of a vector of size 512. This vector is an encoded version which represents each feature that is a representation for the features that each part of the image may have. So as you can see here, the CNN is outputting these FIs, which are then used to calculate the weights that each of these attention networks have. So the weights are calculated by using a fully connected layer, which on this vector, and then applying a sigma activation function. The expression for this is written here. Then we can move on to a coarse representation of the whole image, which is basically the features are combined by taking a weighted average over each of these feature vectors. This weighted average, for now, we will refer to as a coarse representation of the whole image, and a coarse encoding. So this is the first part of the image. This is the self-attention module and can you go to the next slide? And in this self-attention module, we also have this additional thing, which is called the region bias loss. So what the region bias loss does is it is a function on all the weights that is generated by the base CNN that we had. What this loss represents is it places a constraint that the weight that is assigned to each of the part images is more than the weight that is assigned to the whole image. So what we're doing is we are passing the whole image, and we're also passing multiple crops of the image. So this part ensures that the individual parts have more weightage than the whole picture. The margin that we have used for our network is 0 0.1. So what this means is that if the whole image has a weight which is more than 0 0.1 of the maximum of the individual parts, then that will add some loss to the final loss function, and which will get back propagated, and the training will essentially ensure that this does not happen. Uh, Now we are coming to the next part of the network, which is the relation attention module. So what this does is it takes the each of the vectors that we had generated earlier using our CNN, and it concatenates it with the coarse representation of the module. So the new vector that we have, you can think of that new vector as sort of a combination of individual region images, while at the same time incorporating information about the whole picture. So using this new vector will be of size 1024. And this new vector is a fully connected is passed through a fully connected layer again, and again a sigmoid function is used to get new weights. These new weights uh, are then used to next slide. These new weights are then used to find the final prediction of the network, final vector prediction of the network, which is essentially a weighted average over these networks. So the final layer uh, of this uh, of this network is essentially a vector of size 1024, which is the weighted average of all the previous vectors. And finally, this vector is again passed through a fully connected layer, which will predict the emotions. And we are using cross entropy loss along with the previously mentioned region bias loss. So now I'll again show this framework here. We'll show so essentially I'll describe what happened. So first, the image is cropped and divided into several parts. Then the image is passed through a CNN, and we obtain these vectors, which is f0 and 2, whatever the number of croppings that is done. And then finally, these crops are taken an average of which is the coarse representation vector, and uh, and these coarse representation vectors concatenated with the region vectors, which is then passed through a fully connected layer to obtain the final prediction. Uh, the hope in this network is that instead of looking at the whole picture, which may be a projective transform occluded or have a different pose that might be rotated or anything, the hope is that by looking at individual regions instead of the whole picture, the network will be more accurately able to predict what the emotion of the emotion represented by that picture is. Now, can you go to the next slide? Yeah, and finally, yeah, so this is the framework of the picture, framework of the architecture that we have used for the network. Now I'll pass it to Shankar to describe the black box that we had left behind, the base CNN.
Hello, can you hear me?
Yes, you're audible.
The RAM model itself was very simple but very elegant. So what we had not seen was this black box backbone CNN that we are passing these cropped images to. So we'll go a little bit into that. So the backbone CNN that can you go back? Okay, sorry. The backbone CNN that we use, the primary function of that is to extract features from the cropped images. So this is not a novel idea of these authors, and this has been incorporated in a lot of face detection models that have already been built. So generally, a deep CNN architecture is used, and the general trend is to use a residual network because deep CNNs have certain issues that we'll see. And the authors in this paper use ResNet 18 architecture, but there have been considerable improvements since then. So we are going to use the IrisNet 50 model for this backbone CNN. And can you go to the next slide, please? So this particular IrisNet 50 that we use is pre-trained on the MS Celebs face detection dataset. This is because the occlusion and pose variant for dataset is not really that large in number. So when you train a deep model like this, there's a very high chance that the model is going to overfit on the dataset. So training it first on a face detection dataset, which is significantly larger in size compared to this, will help us overcome that problem. So we do that first, and then we take the target data set that we want to train on this, and then use this pre-trained model to find it. Now, what are residual networks? So a residual network is also seen in, but there is a small difference. In the sense, edges need not be between adjacent layers. You can have a layer that has edges going out to layers that are 2 or 3 ahead, typically, and where the intermediate layers are non-linear. So the advantages that this gives over typical CNNs are, in deep CNNs, vanishing gradient is always an issue. But there is empirical evidence to show that if we have edges going not just to adjacent layers but beyond that, then it helps tackle these vanishing gradients. And also the saturation problem which occurs, and a lot of neurons output values close to 0 or 1. So that is also tackled by residual networks. And that's why in general, if you want to train deep CNNs, adding residual connections is a great idea. Since this is pretty deep, it has 50 layers, an obvious choice is using residuals. Next slide, please. Yeah. So the actual architecture of the IrisNet 50 residual network that we use for this problem is displayed above. If we go into the details of the architecture, that in itself is a separate presentation because there are papers written on just the IrisNet 50 architecture. So that particular thing, modulo the fact that we're using residual networks, so the exact architecture of it, we'll try to give a concise idea of it in our PDF, but going into it during the presentation is going to take way too long. So we'll keep that as a black box for now. And for now, all we need about the IrisNet 50 architecture is it works on inputs of size 224 cross 224. So our pre-processing step has to make sure that the cropped images are of this size. Can you go to the next slide, please? So we have used the Python library dlib68, dlib and the 68-point facial landmark detector to detect where the faces are present in complex scenes. So in the FIR data set, not all faces are centered and without any obstructions in the background, or like other objects or like hands present in the background that may affect our training in some way. So to get rid of, not to get rid of images, but to like extract the relevant information from these images, what we do is we use a Gaussian library, which detects the faces and also upscales it to the size of the original image. So doing this has an advantage as well, which is mentioned in the paper. So this upscaling brings out some of the finer details in the facial expressions that were not originally present in the images, and that actually helps get a better accuracy with it. Can you go to the next slide, please? So for our model, the first step is to choose the appropriate number of crops and the appropriate regions of the image that we want to crop. So there are two ways to go about this. One is to choose random crops from the image and see how they perform, or use fixed point cropping, where we, from each of the image, we decide to crop the same regions and see how it performs. So in our implementation, we have chosen the second approach, in which we crop 5 fixed regions and we give these crops along with the original image to the backbone CNN for a feature extraction. Now, this is an example of an image in which we have cropped these 5 parts and then given that along with the original image as well. And our backbone chain will extract features and also give weights to each of these crops that are then aggregated to give one final feature extraction. Now go to the next slide. Okay. So our model was trained on the first training dataset for 70 epochs, and after training, we have used the test data that is also provided to validate our model. So we have used the accuracy score as our primary measure to evaluate the performance, but we have also given the confusion matrix to that is presented in the later slides to give a better idea of what expressions that our model performs well on, and like what expressions, like complex expressions or emotions, that it's not able to capture well. And can you go to the next slide, please? Now we'll present some images that our model tried to predict and the actual classification. The first couple of images are about happiness and anger, and our model also predicted the correct ones. And the next one is contempt, which is sort of a complex emotion, and our model was not able to predict it properly. Can you go to the next slide? And we here have more images, which are surprise and happiness, which again the model predicted properly. And in the last one was surprise, but it did predicted properly. These are some of the examples that we ran, example images that we ran on the train model, and these are the. Now I'll give it back to Ameya so he can share our results.
Yeah. So we actually did this training on the IRISnet 50 model, like Shankar said, and we trained it for 70 epochs, but it took a very long time actually. So we also had to use the CMI GPU, which has 3 GPUs, and even after using that, it took about 2 days, almost 2 days, to get to 70 epochs. So I think I think the paper.
Sorry, how many images did you say you trained upon and tested upon?
We had around I don't remember the exact number, but around 33,000, I think, and about 3,000 for testing.
Okay.
Yeah, so we ran it on the full data set. We didn't run it on a smaller data set. That's why it took that long. So yeah, we did implement we did try out 2 models, like the iResNet 50 and also what was in the paper, the ResNet 18 model. And since it was taking a lot of time, we didn't get to train it multiple times. But in our first training itself, we got a pretty decent accuracy of 86% on all the images. If you take the whole list of plus things, which includes like non-occluded and things that don't have any pose variants also, like clear images, including all of these images, we got an accuracy score of 86, and we can see the confusion matrix on the right. So yeah, so we actually did have unknown as a classification, but I think in the dlib library that used to crop faces, if it doesn't detect a face, we didn't look at that image basically. So in this particular case, we didn't have any images for that were classified as unknown. So we are just showing the confusion matrix for the 8 classes. And
So disgust sort of did the worst, is it? Disgust and
yeah,
contempt, which
so
are anyway difficult to recognize.
yeah, so disgust, I think as the emotions got more complex, it became harder for the model to judge. I think also because it has lesser uh,
And the training data is somewhat biased towards happiness and sadness and other
yeah,
emotions because
it
the
has
data is
lesser
numbered by
emotions compared to,
taggers. So taggers are less likely to vote on contempt.
Mm.
yeah. Uh, yeah, so to verify robustness of our network, as you said, we also specifically looked at the images that were pose variant or occluded. And so we ran on this subset separately to measure the performance. So if you run it only on the images that were occluded and which had some kind of pose variant, we got an accuracy of 81%, which is still quite good considering
Yeah,
the,
this is quite good.
yeah. So
This is, yeah.
yeah, so we have the confusion matrix on the right side for these. Again, here for disgust, as you said, like it doesn't have a lot of images itself. It has only
But
3
yeah,
images.
but anyway, disgust and contempt are two, it's very difficult to, these are also subtle on the face, not,
Yeah,
not very clearly expressed. So that is fine, but the rest with occlusion and pose variation, these are good numbers, I would say.
yeah.
Considering also you have run only 70 epochs, right?
Yeah, although I think even the paper doesn't implement too many epochs. Like we have tried to get as close to it as possible. I think even the implementation, I mean,
Paper
even the
implements
paper,
80, I think.
yeah, paper had 80. We stopped it at 70.
Okay.
This was for actually the IResNet 50 model has like 50 layers, so it takes a lot longer. It takes 2 days to run. The ResNet 18 model ran like reasonably faster. It just took, I think, maybe not overnight, a little bit like maybe 3/4 of a day or so it took for it to run 80 epochs on the ResNet 18. But yeah, this was, I think IResNet 50 got a better accuracy, so that's what we went with. And yeah, I think that is what we had mainly. Uh, yeah, we'll be willing to take any questions now. Hello. Hello.
Hello, ma'am.
I think this
Ma'am
Oh,
had a
she
disconnected.
got a
disconnection.
power cut. Yeah.
Ameya,
Yeah.
by the way, say like we'll provide the code in the
Yeah.
if
Yeah.
anyone wants to look at it, we'll give it the PDF.
Yeah.
Nice. So I have a question, Robert.
Yeah. We can wait, but yeah. And
Back.
huh?
Go back no few slides. Right here. So more, 2 more slides. Next, like the example then.
Wait, you want me to go back or this
Forward.
one?
Yeah.
Okay. So this one.
Tell how the last one is happiness.
Huh?
How did our model classify the last one as happiness? I can understand not getting contempt, but how is it happiness?
I mean, I'm guessing it's because of the way the lips are. I guess that's the best explanation I can come up with.
Fair enough.
There's a box in front of the presentation.
Yeah. I think he opened the Zoom client.
I opened the chat.
I think comes back.
Hello, so I'm back. Terribly sorry about this. I hope you had a discussion with the rest of the audience. Hello?
Yeah. Yeah. So that's
If there
how.
was something going on, yeah, please go ahead.
Oh no. There was just a question about this, about the last one here, as even if it's not contempt, how did it get to happiness? That was the question. But I think like the best explanation I could come up with that was based on the lip arrangement. But like, yeah, it's not a very good. It does fail.
Yeah,
On.
so
It's not a
these,
good.
no, this is very difficult to answer. These kind of
Yeah.
questions are very difficult to answer with deep learning. That is one of the problems with deep learning also. So, I think I was telling somebody before that, you cannot say why something has happened out of a deep learning model. And so that is why there are concerns in law about it. How will you explain why something happened? So,
Yeah, we just wanted to show the limitations of our model as well. That's why we put this.
Yeah.
yeah, that's okay. That's a nice way of spinning it. Uh, yes. Yeah, you can go ahead. You had more to show.
No, ma'am. I think this was where we had. Were you? I'm not sure when you actually left the meeting, but
Yeah,
like,
I was here. Yeah. I was just saying that this is pretty good.
yeah,
But
I think this is
he
all
was,
we
yeah.
had for.
Okay.
So we didn't choose to show the code because it's kind of there's a lot of code and it's not very organized, so it'll be hard to explain. But we'll try to clean it up a bit and put maybe snippets of it in our project report.
Okay. Yeah, no problem. Unless somebody has a question about the code, I don't have a question, but anybody wants, then only. Otherwise, I'm okay with you putting it in the report only.